Class, we're doing 4.2, inflection points. Inflection points are points where a graph changes concavity. So don't get these mixed up. A critical point is where the slope's zero, okay? A max or a min, but not always, as we talked about, it could be at where it's undefined. Points are where the graph changes concavity. And if you look at this is something we like to know because this is going to tell us where it's going the fastest, either increasing or decreasing, okay? That's going to be the steepest slope at that point, and that's why we like inflection points. So if you think about this, when we talked about second derivatives, if we had concave up and concave down, the inflection point's going to be where it changes concavity, okay? And some of you guys had this on a group project, and I noticed some of y'all looking at that and saying, I guess it's still not that great to see. Yeah. And looking, already kind of looking at that inflection point of where something, I don't remember what the project was, but where something was growing fastest. And I saw a bunch of you looking there, and that's what you're looking at, is the change in concavity. So the second derivative must change signs. So to find inflection points, find where the second derivative equals zero. So Corey, you can't get out of always not finding second derivatives. Yeah, and then we also check to see if the second derivative is changing. So I can start to see I need to move things kind of in the middle more. So if I have this same function that we just did, we just found the first derivative, again, 3x squared, 18x, 48. Found the second derivative, 2 times 3 is 6, and then 18, constant 0. If I set my second derivative equal to 0, this, okay, so 16x, and x equals 3 is a possible. That's the only weird part of this section. Something else could be happening, and we'll learn what that something else is later. But this is a possible in x equals 3. Once again, a point isn't just an x value, so you really need to get the xy coordinate. And remember, you just plug this back into your original function. Again, just from teaching this for so long, that's probably the biggest mistakes I see students make in this section. When do I plug the number into the derivative? Well, if you want to know if it's increasing or decreasing, because the derivative tells you the slope, right? When do I plug it into the second derivative? Well, if you're looking at concavity, right? If I want to know the actual value of the function, then you just plug it into. And so I can actually look at this graph that we saw earlier and plug that point in and say, yeah, that makes sense. This is where it's actually changing concavity.
What graph?
Good gosh, what's up with the blue? What? That graph. What? Can you see the points okay? Yeah. Wow, you can't even see some of the words. These are like taking screenshots out of your textbook.
Because of the lighting.
So hold on.
The possible inflection points include the two maximum and...
No. Those are still your local max, local min, your critical. So the inflection is only that point right there. It's only where it's changing concavity.
Yes, but it said there's 3 possible. What does that mean?
No, x equals 3. In other words, that was our 3. Our 3, I think that's what you're saying, the 3 was our x value.
Okay.
Yeah, just one inflection point on this one. And this is certainly something you would want to graph, okay, to see, does that make sense? Well, yeah, it makes sense. Okay, so now up here, all I did was plug in, if I plug in values, and this is makes Corey happy again, I plug in values to the left of it, I plug in values to the right of it, so I can see that, and it doesn't matter if you can't see this anymore, I can see that the second derivative changed signs in between the inflection point, x equals 3. If I look to the left of it and to the right of it, and it changes signs, that proves it's an inflection point. Okay, where the second derivative, because again, remember the second derivative is telling you, that's telling you concave down, and that's telling you positive concave up. So that would make sense if you have a negative and then goes to a positive. All right, a surge function, and there's actually an entire section coming up on this. So this is going to be one of these like there it is, but we'll examine it later, probably even next class. So a surge function displays an initial linear growth, okay, you know what linear means, and then followed by exponential decay. Okay, so something grows very quickly and then it starts to decay. They're used in modeling situations where there's an initial input of a substance into the system at a constant rate, okay, could be a drug, and then of course we hope it's going out of your body, okay, the elimination of it. And so here's a good example of drug into the bloodstream and then leaving your body. So this would be a perfect example of what a surge function would be used. This is what they look like. This is what they look like, meaning that they start linear, okay, and just shoot up very quickly and go exponentially till finally they top out a max. I mean, this again looks just like when we did the example with Vivian with the deadly needle. And then after it tops out at a certain time, and you're going to see later, you could have some of these continuing, because what if it's somebody that every day you have to take a pill, right, for something?
So every day I get stabbed by Vivian?
Every day you get stabbed by. Yeah, your doctor. And so we could see that this hits a max, and then it comes down a little bit and might hit another local max because you're continually taking this pill. This is, can you even see that? No. The function is C equals ATE to the minus BT, where of course this is your exponential piece and this is your linear piece of the growth. Again, we're not going to examine the function this section. I believe it's 4.7 that we actually look at this function. Kind of can see that one because it has more dots. This would be a good example of, I hope none of you smoke in here, but if you do, if you have nicotine, you know, and then you stop smoking for a little while, of course the nicotine's leaving, the nicotine concentration after smoking a cigarette. Okay, so again, any type of body. All right, that was a surge function. And this is why you can see our next lecture, we do surge functions and logistic growth. They kind of go together. A logistic function starts growing slowly, okay, and then it'll start to increase, and hopefully you can kind of see there, it's going to increase at the inflection point, okay, because it's changing concavity. And a lot of times you'll hear these just called S-curves. And so if I draw the curve out here, this is what the actual function looks like. Again, we'll examine next class the actual function. And so you can see that it starts out and kind of looks like an exponential function. Where it changes concavity, I can actually get this value by getting this top value where it tops out. This topped out value is called the carrying capacity. This is like something always, I don't know why I think of this because I don't have a fish aquarium, but if you had a fish aquarium, what happens? You get two, I guess you need two, right, to have babies. My mama taught me that. Yeah, okay. So anyway, you got a couple of fish in this aquarium, and then bam, babies. Well, the aquarium's only so big, and then it starts to top out, which is called a carrying capacity. A carrying capacity, this is perfect for any population. I mean, you get to the point where nobody else is going to fit in San Antonio. Y'all got to move out, right? And so that's what carrying capacity is good for, is populations, because pretty soon you get too many in a population and some start dying out. Again,
Like, let's say we kill each other off.
Or kill each other off. And again, I think of a fish aquarium because if you have a bigger aquarium, you can have more fish, right? And so your carrying capacity could be restricted depending on your aquarium. And so here is the population of the U.S. from 1790 to 1940. As you can see, it starts slowing down. Why? Because somewhere in there was the invention of the pill, right? And so, in other words, like I said, populations are perfect for this type of a S-curve or logistic function because you can start to see eventually you're going to have to start slowing down. And that